the plan for today is to talk about the orbit method. I will first talk about the original work of Kirillov, which is related to simply connected nilpotent Lie groups. Then I will talk about the exponential map a little bit in great enthusiasm. And then I will talk about Howe's p-adic version of the orbit method. Let me just remind you, it's always good to remember why are we doing what we are doing. So we proved, well, most of the things that I could prove here, that if I'm taking an arithmetic group and I want to look at the zeta function, it has an ordered product decomposition. That's a theorem by Larsen and Lubotsky. You take the complex points and you look at the zeta function, and here you take the dimension of K over Q. So K is always a number field and O is the ring of integers. And in the background, we always assume the congruent subgroup property. These are the, excuse me, these are the entrance fee to the game. Because without that, we don't have this order product decomposition and we can't say much. So here we have product over all the prime ideals, zero ones, and then the zeta function of the completion at the prime P. And there are many adjectives attached to G. G should be semi-simple, simply connected, connected. And these I just didn't go into them. You just pick your favorite group. And as we said, the interesting or the difficult representations are those that are coming from these groups, and they are, all of them are p-adic analytic. So they sit inside some GLD ZP. And we can always look at the reduction of GLD ZP to GLD FP, so the reduction modulo P. And the kernel, which is called the first congruent subgroup, this is the, the kernel. This is a p-adic analytic pro-P group. The kernel is pro-P, simply because it is the intersection of G of OP with the first congruent subgroup of GLD-ZP. And this group here is a pro-P group. And so we're getting here a pro-P group. So it's a p-adic analytic and pro-P. And that makes it very special, in particular, amenable to the orbit method. Okay, but before I talk about the orbit method in this specific instance, I want to tell you about the original work of Kirillov. I think it's always instructive to know the history where we are coming from. We don't always have the time to do that in life, but you now have the time. That's the part in your life where you have the time. I know you don't think about that. You don't see that in this. You don't think that you have time, but you're very busy. But now you have time. So to read on things which are slightly, they're not exactly your research. You can just expand. Right. So let's talk about Kirillov. So Kirillov in the 1950s, he constructed a method to find the irreducible representations of an nilpotent, so simply connected, nilpotent Lie groups. So they sit inside unitriangular upper unit. You can think about them as sitting inside upper unitriangular matrices. And the good thing about them is that when you look at the Lie algebra, if this is the Lie algebra, then the exponential map is a bijection from the Lie algebra to the group. And not only that, it's a polynomial map because your matrices are nilpotent. And so when you take powers after, when you reach n, the dimension, you get 0. So the exponential map becomes a polynomial map, and it's a bijection, and you have the inverse, which is the log map. And you have an action of G on the Lie algebra, and therefore you also have an action of G on the dual, on functionals. And this is the action which is interesting here, the co-adjoint action. So the action of G on G star is called this is the adjoint action, and here the action is the co-adjoint action. And what Kirillov proves is that there is a bijection between the unitary irreducible representations of G. So these are unitary irreducibles, and orbits of G on G star, between irreducible representations and co-adjoint orbits. And so let's denote by, if you have here an orbit omega, it will map to a representation rho omega, and I'm going to construct this representation now. So how does it work? You take a representative. So here's the construction. You take an element in omega. So this is a functional. So omega is a coadjoint orbit. So it's a subset here. So this F here is simply an element here. It's a functional in the Lie algebra. And one can associate to be a bilinear form on the Lie algebra. And this bilinear form is defined by, you take X and Y, you map them to the commutator, the Lie commutator, and then you apply F. So you have an element of the Lie algebra, and you can apply F, and you get a real number. And it gives you, it's clearly bilinear. We have a functional, and we have the commutator map. So it's a bilinear map. And it's an alternating map, right? Because the Lie bracket, when you swap x, y, it equals to minus yx. So it's an alternating bilinear form, and therefore it has a radical. You can look at the radical of the form. So let R F be the radical of the form. So these are all the elements Y, such that Y in G, such that they are orthogonal to all the other elements. So BF of XY is 0 for every X in G. So this is the radical of the form. And now it turns out that the radical is a subalgebra. So not difficult to show. And you can exponentiate it. And and get a subgroup. So RF by definition is the exponentiation of RF. So the good thing here with the group and the Lie algebra, when you look at the construction of Lie groups and Lie algebras, you have always the map from the Lie algebra to the group by the exponential map, but it's not a bijection, and it doesn't give you a bijection between algebras and subgroups, but here it does. So you have here a subgroup, and this subgroup also turns out to be the stabilizer in G of the functional F. And let's draw some picture here. So what we have here, the group G, and we have the Lie algebra G, and we have the exponential map. We picked a functional, so we have our functional here, and we have the radical of the functional. It's a Lie sub algebra of G. We exponentiate the radical, we get a subgroup here of G. That's what we have so far. And now it turns out that there is, so by the way, sometimes you can do simple exercises and see everything. So, or many things. So one of exercises for today, I'm talking about exercise 18. So I'm sure you've seen parts of that, and if you are fluent in symplectic forms, then you can move on to the next question, which is I'm trying to convince you to be fluent on symplectic forms on abelian groups. And if you want more challenges, you can go to non-abelian groups. You can find your way there. But the nice thing about symplectic forms is that there is only one symplectic form up to conjugation. And if you have an alternating form, so a symplectic form, and let me remind you, is an alternating bilinear form which is non-degenerate. And if you only take alternating forms, you will see that you can always conjugate an alternating form on a vector space V and find a basis such that the matrix is block diagonal with these 2x2 blocks. And if you want it to be non-degenerate, you just get rid of the zeros here, and therefore you get only one symplectic form. And what you can show is that there's a notion of a maximal isotropic subspace. So an isotropic subspace with respect to a form is a subspace such that the form vanishes on that. When you restrict the form to that subspace, you get the zero form. Okay, so let's go back to our story here. I have this form here. What I'm claiming is that there is a subspace of G such that if you restrict it to the subspace of G, you get the zero form. I mean, there are many subspaces like that. The radical, for example, is such a subspace, but our radical is even more than that. It vanishes. The form vanishes when you restrict it to the radical cross G. Yeah, the whole point of the radical is that it is orthogonal to the whole Lie algebra. So if you restrict the bilinear form here to the radical cross G, you get a zero map. But we're interested in a isotropic subspace. So let me give you some definition. So isotropic subspace. It means that BF of H is zero. And we say that it is maximal if it's maximal with respect to inclusion. And if it's an isotropic and maximal, and then it will be called, okay, let me, I need some more room because I have some more names here. So isotropic and maximal is called Lagrangian. Sorry? And it will be exactly the half dimension of the space. That's your exercise for in linear algebra. For those who have not seen it, exactly. Thank you. And that's important, as you will see here, and even more important. Yeah, it's important here, and it's important also in what's happened next. And if it's in additional, if this is not just a subspace, if this is a Lie subalgebra, then it's called. Okay, just make some more here. So this is Lagrangian. And if you have everything here, then this is called the polarizing subalgebra. Okay, so let me just change my diagram a little bit. So I can have here a subalgebra, and such a polarizing subalgebra always exists. Okay, Kirillov proved that. So I'm giving you the sketch of the construction without the details. And in my notes, I'm referring you to where you can find all the details. Many of them you can just do by yourself because it's really, it uses natural things. Now, such a polarizing subalgebra, as Davud said, is half of the dimension of the space. So what we have here, this is the quotient here is finite dimensional. It has to be even, right? Because symplectic forms are even dimensionals. They're only on even dimensional spaces. And we have a maximal isotropic subspace, which is half of the dimension. Here, it's not only a subspace, it's a subalgebra. And it's called the polarizing subalgebra. And we can also exponentiate this one to get a subgroup here. Now, questions? Hawaii?
You mean Lagrangian, like when you quotient by the radical?
Yes, yes. The polarizing question is the polarizing algebra unique? No. No, it's not unique. Thank you for the question. Yeah, yeah, you're right. So I'm modding out by the radical. At any point I can just kill the radical and don't think about it. All right, so now with all this information, we can now construct representations. So what do? We continue this map here with the exponential map. So now the exponential map in the good old naive sense, taking the real numbers to the complex unit circle. Okay, that gives us we now have a complex character of G, of the Lie algebra G, and here we have the log map. So we can now. Something is wrong in the directions. Okay, it should be okay, but I now want to define a character of H. So theta F H. So just remember, we made many choices here. And let me also, since if you see this for the first time, let me just again remind you the context. So I'm trying to convince you that that there's a construction by Kirillov that gives a bijection between unitary irreducible representation and coadjoint orbits. Okay, I'm trying to convince you that this is a plausible thing. So I'm taking an orbit, a coadjoint orbit, but I chose a representative of the orbit. And with this representative, I computed the radical and the bilinear form and whatnot. And then I chose a polarizing sub algebra, and then I exponentiated. But at the end of the day, I chose a subgroup H. So that's also a choice. So I'm just trying to remember what are all the choices that I made here. And now I can look at so every point in G is of the form exp of X. So depending on your point of view, if you want to write an element of G, or so every point here is exponential for an element in the Lie algebra. And now we are defining the character to be just e to the 2 pi I f of x. Okay, if you prefer the log, then it will look like that. It will be theta f h of g. That will be e to the 2 pi I f of log g. Yeah, so at the end of the day, I'm just composing all these maps, and I'm getting, oh, but not here, I'm doing it here. Well, I'm doing it like that. Then get the log, I have the embedding here, I can take f, and then I can map it to S1. Okay? Now, you can ask, how do I know, sorry? Yes, you can ask, is theta a character of H? Excellent, good. So, yeah.
What does a character mean for us in this sense?
A character, a continuous one-dimensional representation.
Okay,
Is it? Yeah, it is, because because you can show, I think it won't even, it's a really easy that if you take the commutator, the Lie algebra commutator, and you exponentiate it, you get the group commutator. Okay, and then so, and the fact that yeah, okay, there are a few things to check here, maybe, yeah, but at least what you can see, I mean, f vanishes on the commutator, right? Sorry, f vanishes on yeah, on the commutator, right? This is exactly where this is, we took an isotropic subspace, and therefore this composition vanishes on the commutator of H. So at least it's plausible now that a function that factors through the commutator at least has a chance to be a character. Okay, but it is a character. And now what you can do, you can induce it. So rho FH is now defined as the induced representation from H to G of this character. Okay, so so we got ourselves a character at this level here, and we induce it to G. And if we were in a course on Lie groups and representation of Lie groups, I should have spent time to tell you what I mean by induction here. Okay, so this is a unit. We need to produce a unitary representation. Okay, there's an analysis coming up exactly here. Okay, so far everything was linear algebra until now. So Lie groups, Lie algebras, exponential map, kind of soft computations with that. But now that's really the point where the analysis come in, because this is now going to be an infinite dimensional representation. It's these are all Lie groups, and the dimension of this one is half the dimension. Well, yeah, Joel looks at me and he was right. I mean, the dimension of this quotient here is twice the dimension of this one. And so there's much to be said here. So that's the point where analysis gets in. But since I'm going back to p-adic groups soon, and over there things will be finite, really finite, then I will not need to worry about that. It will be representation of finite groups. So I don't want to get into too much to that. But now the point is that this construction, so first, this actually, so there's a claim here that this here actually depends up to isomorphism only on omega. Okay, so there's a claim here. I'm not writing it in a nice way. Yeah, it means that if you choose different f and different h, it will give you the same representation. So this is a this representation up to isomorphism depends only on the orbit. It doesn't depend on any of the choices of the character and of the subgroup. And now the statement is that so claim that this is independent. Okay, let's do it like that. I will define it like that, and I will say that this is independent of f and h. So that's one claim, and then another claim is that rho omega 1 is not isomorphic to rho omega 2 if omega 1 is a different orbit. So here I should say this is a unitary irrep. So this is also a claim. Yeah, I induced and I didn't tell you that it is irreducible, but it is. And the fact that we induced from a maximal isotropic subspace, that's the point where the irreducibility comes into the game. If you could play this game by inducing from something smaller, which is isotropic but not maximal. But if you go up to the maximal one, that will guarantee that your induction is irreducible. No. The question was, is this H normal? And no, it's not. In general, it's not. No. All right, and so these are disjoint, and the last claim is that all unitary irreducible representations of G are obtained in this way. Okay, that's Kirillov orbit method. It tells you, it gives you a prescription to find all the irreducible representations of an nilpotent group. It doesn't mean that you can really do it in practice always, and but it gives you a linear way. Also, importantly, if we kind of go back to the statement itself here, it gives you a linear way. So this is a linear space. It gives you a linear environment to think about representations of a group. It's a okay. So that was I think even more than I planned to say on the orbit method for real groups. Are there any questions? Yes.
What's the analogy when you, instead of H, you got the Borel and also induce representations?
Analogy, instead of H, you
have the Borel.
Yeah. So the question is, what happens if I replace H by the Borel subgroup? This is a great question. Let's talk about it afterwards. So I don't have a simple answer to you, but you are asking a fantastic question, because I can't even say it. Let's talk about it later. So, okay. Okay, that's it for Kirillov, the history of Kirillov, and now I want to talk about the exponential map. So I gave you a few exercises about the exponential map, and this is the heart of the matter. This is the properties of the exponential map and the log map and the interaction between them. This is the reason that Lie algebras are so useful in the study of Lie groups, that they carry so much information. Those of you who've seen the development of the course in Lie groups, in Lie algebras, how many of you have seen that? Okay. How many haven't? Okay, let me say something about that. Okay, I'll go back to this soon. So when you study Lie groups, so here's, suppose this is your Lie group. So Lie groups are manifolds so we talked about topological groups, but Lie groups, the structure, the functions, multiplication and the inverse, they are smooth maps, and the group G is a manifold. Then you can take the tangent space at the identity. This is similar to what you're doing in Things course, except that here things are more concrete and you can look at them. The definition of the Lie algebra is very concrete. It's the tangent space at the identity, and the exponential map takes you from the Lie algebra to the group. And if I separate the Lie algebra and write it here, and this is the 0, then it will take a neighborhood of 0 and map it to a neighborhood of 1 in a homeomorphic, in a smooth way even. And what you can show is that the group structure is really defined by the Lie algebra. The local group structure is completely defined by the Lie algebra structure. And the reason for that, and that's the reason for the essential role that the Lie algebras play in the theory of Lie groups. And that's where linearization really helps you to classify. So how do we classify Lie groups? We classify the Lie algebras. It's easier to classify a linear object than algebra. Then you have all root systems and what things that you will see also here. But the key here is this formula here, which I hope you played with that. This is the first 3 terms of a very famous formula called the Hausdorff series, or Campbell-Hausdorff series, or Baker-Campbell-Hausdorff series. If you want your name, we can also edit. So it's let me just use the shortest one. So it's the Hausdorff series. And the miracle is that if you take the algebra, the associative algebra generated by 2 non-commuting elements, the free associative algebra on 2 generators, you complete it in the same way that we completed the p-adics to get the p-adics. You look at infinite sequences and you allow them, you put them into, in my notes I gave you some more about that, but you complete it, you allow infinite series. Then you can think about the exponential map, these 2 power series, the exponential map and the log map, and then you observe that the log of the product of the exponent. So note that if you know that t and s commute, then the exponent of t times the exponent of s is the exponent of t plus s, and the log of that is just t plus s. So if t and s commute, you don't see all that. But in general, you'll get a power series. This is a power series. This is a power series. You substitute in log, you get a power series. And the miracle here is that this power series, which could have been crazy power series in this algebra, is you only see commutators. The higher terms are also commutators. Okay, and let me write this one as a theorem. So so the theorem says that if you look at function h, let me use xy here, which is log of the exponent of x, exponent of y. Yeah, this is in Q. Then this is a sum, is x plus y plus the commutator plus 1/12 xy, and then y plus minus 1/12 xy commutator, and then commutator with x, and etc. And it's all Lie commutators. Okay, this is the key, because I mean you see it says that. Let's see what it means. Here's exponent of x, exponent of y. It says that if I take 2 points here and I map them into the neighborhood here, and I multiply them here in the group side, group multiplication, and then I take the log, I go back here, I get something which only depends on Lie commutators. And that means that the Lie algebra knows about the multiplication here completely. Okay, that only can be done in a neighborhood of the identity. So in this sense, the Lie algebra only see a local behavior of the Lie group. But this is exactly where the transition from Lie groups to Lie algebras occurs. So that's the first part of the theorem. That's the first part, that if you, in the first course in Lie algebras and Lie groups, you probably see only that. The second part is something which you don't usually see if you're not interested in p-adic or in finite groups. And that's kind of the extra miracle that you see with the exponential map. And it says the following. So if I write down now this as sum of hn of x, y, and goes from 1 to infinity. So that counting the degrees. So this one will be h1, this one will be h2. So I'm always getting homogeneous expressions, sums of homogeneous expressions in Lie brackets. That's what we will always see. So this one is also here. So if I'm writing it like that, and if I'm writing a basis of these coming from these monomials, so I'll write each of the HNs. So say that Hn of xy is a sum over alpha of a n alpha, e alpha, where the E alpha, this is a basis of simple commutators. So this E alpha is the basis of homogeneous. I think I need also an N here. Of homogeneous degree N. Just keep track of time. So each of these HNs, I can write it as this is the homogeneous kind of the nth homogeneous piece of this sum, and I can write it as a sum like here. I mean, I have two expressions. So here the E3 I have for E3 alpha. E31 and E32 I have, and the coefficients are 1/12 and minus 1/12. Is this okay? You all happy with what's going on here? Okay. So in this case, one can show that let P be a prime, any prime that you want. For every prime P, the valuation of A n comma alpha is greater or equal to minus n minus 1. No, exactly to minus n minus 1 over P minus 1. Sorry? Ah, right. Was this like that all the time? Thank you for saying this. All right, so what have you missed? Okay, so you haven't seen all the, okay. Okay, let me start. I can now give you only, I can give you now only a talk on this part of the, okay. Sorry? Two windows? Oh, you know what? I know what I should have done. Silly me. Well, I need the correct mouse.
It's fine here, right?
Start from the beginning.
We could
Okay.
see, hello?
Yeah.
Okay.
What have I done?
No, it's good. We could see the entire screen the entire time. So I think it's just the Zoom settings that you can change.
Zoom setting. Yeah. Silly me. All right. So that's something which if you only care about real Lie groups, you don't care about this coefficient so much. You only need to care that they're converge. But now I'm thinking about them really as happening over the rational numbers, and I observe that there is a bound on the denominators. So these denominators, they can't grow arbitrarily large. So in particular, if I'm confining myself to a p-adic, a specific P, and I'm taking a deep enough congruent subgroup, P to some power, as if you have looked at the first exercise here, or maybe the second, then when you are trying to solve this exercise here, you see that the exponential map converges, right? And the reason is that we have this bound here. And then if we just look at what happens when you put P to the N, X to the N factorial, that's the general term in the exponential map, we get that this is greater or equal to 0, so things will converge. So that's what I mean by deep enough. So if I take a P or P square of an element, then that will converge better, right? As deeper as I go, things will look better. So So that means that now we can apply this in a periodic setting, because the fact that this that we have all the nice properties of the exponential map and the log map and the relation between them doesn't see convergence. So it only sees the convergence that we decided to see here. Yeah, I chose to look at this point here and kind of filter my algebra and complete it, but this was my choice. I can so things will be defined, but other than that, it's just I don't need anything else. And so the only issue that one needs to worry about with the exponential and log map, because they behave well in any environment. You don't need to say even the exponential map and the log map. You don't need to think about them as maps. There are elements in the ring, and you can substitute in a very abstract way. They don't go, they are just there. So so now we can just apply this into a periodic situation, provided the things converge. And this exactly tells you the thing can converge, because if you now take x to be a multiple of p, or p squared, or whatever you need, then you see that these things will just converge, because the coefficients don't grow too much. And so I have 4 more minutes, and I will now go and tell you a little bit about I mean, in a way, I now told you exactly what Roger Howe knew when, well, he knew maybe other things. I'm sure he knew other things. But if you're Roger Howe and you're thinking that you want to do a Kirillov orbit method for the p-adics, then you stare at this kind of condition here, and you take your favorite p-adic group and you try to work out what can go wrong, and then it doesn't. Nothing goes wrong. You can just do it. That's not precise. So some things can go wrong. What can go wrong is that this beautiful Lie correspondence can be a bit tricky. So now, okay, let me say a little bit about how p-adic version. So what is the setup? You take G. Take G to be a pro-P p-adic analytic. And therefore it sits inside I plus P times MDZP. Well, not exactly, right? Because in GLDZP, you have the upper triangular unipotent matrices. It's not. So I want it to be like that. Yeah, I'm choosing it in this way. It's not a big compromise. And now I have the log map, and that takes me to PMDZP. The log map as a power series. And your exercise, the exercise that you did for ZP, works here as well. You just need to see that it works in the non-commutative. So you need to adjust your solution and see that it also works for matrices. And the log and the exponent, they must be now inverses to each other, because as form a power series they are. And now you can define a Lie algebra by taking the log map and the exponential map here. And now you can just start and play the game. You want to construct the irreducible representations of G. Then you take your group G, you take your Lie algebra, and you have your exponential map. And now everything is p-adic. Now you take a character of the Lie algebra. So you look at G. So this is the first change that we do. Before that, we looked at R star, And here we need functionals. Here we need to take already here we need to take the Pontryagin dual of G. So remember, I composed things with exponential map at the end, like from the real numbers to S1, and then I'm already taking things composed with that map. So I'm looking at unitary characters of the Lie algebra, and then I'm defining. You know what? I don't want to rush this. I will take 5 minutes tomorrow, and I will complete this tomorrow. So what I will do tomorrow, I will build on all this intuition, and I will explain the p-adic version very quickly because I've given you all the background. And then I will move back to zeta functions, and I will show you how we can use this information to write the zeta functions in a very neat way. Let me just sell you more exercises, trying to convince you to do them, so that you will be completely ready to what we are doing tomorrow. So I gave you. So here's an important group. I don't know if you managed to compute the zeta functions of these two groups. This is a solvable group, which happens to be a semi-direct product. So that is an easier exercise. This is a unipotent group, the Heisenberg group. Can you write the zeta functions of these representations, zeta functions of this group? So compute all the irreducible representations of these groups and write down the zeta function. And you can do it with your own, okay. There is some sophistication here, and I'm happy to be around here to give you clues if you want. And then you can do this using the orbit method. Even though this is a finite group, finite P group, and that's the miracle of the exponential map that I was talking about. You can adjust this into situations where you wouldn't. I mean, we started with the real numbers. Everything was very, very analytic and very, very continuous, and you can apply this to P group, to finite P groups, and you can just do it. You can find a Lie algebra corresponding to this thing by using the exponential map. You need to worry about the characteristic a little bit. You don't want the coefficients to blow. You don't need to see your characteristic coming as a denominator. So you need to restrict your attention to higher primes. Okay, you do that, and then you can use the orbit method to find the representations of the Heisenberg group. So all that coming up tomorrow. Sorry for taking more time. Thank you. Questions? Yeah.
Is there like an interpretation of the?
Yes.
Can you tell me what it is?
Yeah, I want to encourage you to look at well, I'm not an expert on that, but it's a long story anyway. Even yeah, so you can have a look at Kirillov's. He has books. One is called Lectures on the Orbit Method, and there's also a paper. It's called Merits and Demerits of the Orbit Method. They're all written very nicely. Many examples. And that's what's very nice there. All the time there's examples you can compute and you can see what's going on. And he discusses all these points of view, like symplectic. There's a lot of symplectic geometry going on here. Absolutely. More questions? Hawaii?
No.
No. Okay. Thanks.